Hello, welcome to Mickey Techie. Learn as an engineer, teach like a champion. I would like to thank my family for their continuous support and the encouragement towards of creating these kinds of technical videos and publishing in the public domain. And I would like to thank my mentor, Professor R. Surendran from Government College of Technology, Coimbatore. And I would like to thank Almighty for continuous support on my good health and prosperous mind. And I would like to thank my followers and subscribers and all my dear students. Today, the topic of interest is shear stress in beams. This is a very important topic. We are generally in engineering, most of the applications are considered as a beam and solve the analysis. We can name as an example like a four-wheeler automobile or a bike, two-wheeler vehicle. It is considered to be a simply supported beam, and whereas the heavy trucks are considered to be an overhanging beam. And for the chassis, as a overhanging beam and a simply supported beam, to solve the bending and a deflection and torsional shear stresses for the chassis. In this criteria, the shear stress in beam is very important. We can similarly we can call it as a many examples like a table, a dining table, or a bed, or a teapot, or a sofa, whatever we call it as, it can be considered as a beam, and we can solve the shear force and bending moment and shear stresses developed in the beams. We can easily find by means of these formulas and this theory background. And we know that all the automobile chassis are either in the shape of a rectangle or a square or a triangle or a circular section. So these four sections are very important while considering a chassis design. Why means, let you know, the shear stress produced in the rectangle section is shear stress tau is equal to F A y bar divided by I into B, where F is the shear force. We know that shear force is the vertical force acting at a point, and small a is the area of the beam, and y is the distance from the distance of the center of gravity from the neutral axis, and I is the moment of inertia, and B is the width of the beam. Here we are going to take three beams, rectangle, square and triangle, and for them we are going to find what is the ratio of maximum shear stress to the average shear stress. All are equal to 3 by 2. That means the beam section of rectangle, square and triangle all are having a same ratio, that of the maximum shear stress to the average shear stress is equal to 3 by 2. Here I am going to make how the 3 by 2 and how the calculations are going to do, and what is the shear stress diagram in the beam, that I am going to explain. Okay, first of all, consider a rectangle of a width of B and depth of D, and this is the neutral axis. Okay, so this is the neutral axis, and we are going to consider a topmost fiber means it is the distance, the top is in the distance of d by 2, and y bar is the distance between the center of gravity of a form neutral axis, this to the neutral axis. So this is neutral axis, NA is the neutral axis, and this is the portion, and here is this EG. So this distance is called as y bar. Okay, so it is subjected to bending. What happened? What happened? The bending, shear stress, and the outermost fiber, the outermost fiber and the innermost fiber. This is the outermost fiber, and this is the another outermost fiber are having zero, and the innermost fiber, the shear stress is maximum. That means at the neutral axis, the shear stress is maximum. Where the shear stress is maximum? At the neutral axis. The average shear stress is somewhere between these, between here. That is why the ratio of this thing to this thing for a rectangle section or a square section or a triangle section, it is 3 by 2 ratio. Here, the shear stress variation along the rectangle beam is in the form of a parabola. This parabola condition will be true for the rectangle, circle, square, and also triangle. Next, the shear stress in the circular section. If the circular section means tau is equal to F divided by 3I into capital R square minus small r square, and where the capital R is the radius of the circle and y is the distance from neutral axis. The shear stress diagram for the circular section, it is similar to parabola. Here you can see it is similar to parabola. Whether it is a circular section or a rectangle section, when it is subjected to bending, the minimum or a zero shear stresses in the outermost part and the maximum at the innermost fiber. Therefore, here the ratio of maximum shear stress to the average shear stress for the circular beam is 4 by 3. Here we are going to discuss shear stress in triangle beam. Triangle beam tau is equal to 8F divided by 3BH. It is also a parabola where the neutral axis is not at the section center. The neutral axis for the triangle is at the section of the medians. Okay, here the size is h by 2 and h by 2. Therefore, the average is of 3 by 2 ratio. That is, tau max divided by tau average is equal to 3 by 2. Therefore, 3f divided by bh square. bh. 3f divided by bh. Next, the square beam of a different orientation, like a diamond shape, what will happen? The neutral axis will pass through the one of the horizontal diagonal. The horizontal diagonal will have a smaller amount of shear stress. Okay, so these sections are very interested, where if the square section, if we are having a square section, means the shear stress distribution is in a parabola. That means the neutral axis having a maximum amount of shear stress, where if the orientation is slightly varied to a diamond section, what happen? The neutral axis, there is a minimum amount of shear stress. In the neutral axis, there is a minimum amount of shear stress. It indicates that instead of square section, the diagonal section will carry a maximum amount of shear stress. That is why the ratio of the maximum shear stress to the average shear stress is equal to 9 by 8, where in the previous this for the square section, the tau max by tau average is equal to 3 by 2. Here it is 9 by 8. Okay, and here the shear stress is equal to 9 by 8 f by a square, where d is equal to a root 2. And the next very important section, it is shear stress in I section. You can see the I section, the most of the heavy vehicle, the cross member, chassis cross member are in the form of I section, and also you can, if you have a chance to dismantle an engine, you can see the connecting rod is of the I section. Here, the I section, the maximum shear stress is produced at the web section, that is at the neutral axis. Here, the flanges having a minimum amount of shear stress where the web is having a maximum amount of shear stress. Therefore, we have two different forms of shear stress. One is at the flange and another one is at the web, where the flange tau is equal to F divided by 8I capital D square minus small d square, where the shear stress in the web is capital B by small b into 8 divided by, F divided by 8I capital D square minus small d square. Here we have an important note which gives for the triangle section tau is not maximum at the neutral axis but in the maximum depth of b by 2 from the top. Okay, and for the T section, the maximum shear stress is at the web. The shear stress is maximum at the neutral axis and minimum or zero at the outermost fiber. Here from this we are having an interesting topic of the shear center. What is meant by a shear center? It is a point in or outside the inside or outside a section through which the shear force applied produce only no torsion or non-zero bending. Non-torsion or non-zero bending, that point is called as a shear center. You can see that in the shear center there is no torsion as well as no bending. The bending, it is an interesting phenomena on the neutral axis of the beam. At the neutral axis there is zero bending, and whereas the shear stress is maximum, therefore neutral axis is not a shear center for any beam. That you have to understand, and I hope that you have enjoyed the video and a good amount of knowledge is transferred, I hope. So, if you have any doubts, you can let me know in the comment section. Thank you. Thank you all. Please share and subscribe the video. Thank you.